Okay, so I think we can uh, finish the break and resume our discussion. So let me share the screen again. And as usual, if something is not working, if you cannot hear me or if you cannot see me, just let me know in the chat window. And by the way, so the recording of the first half of today's class, it should be already visible, available on the Moodle page in the Panopto menu. And the Zoom one will be also available in the Zoom menu at the end of the class as well. So in general, for each class, there will be two recordings, two Panopto recordings for each half, let's say, separated by the break, and one Zoom recording for the entire class as well. Okay, so let's continue our discussion. Now moving to the data model. So why do we talk about relational database management systems? Why relational? Well, simply because they rely on a specific data model, which is the relational data model. In real world, as we said before, applications will model uh, some real world information, some data in terms of entities and relationships between those entities in general. Entities such as actors, movies, and relationships such as who played in what movie and so on. And there are, of course, various ways, various alternatives for how to model such real-world information. And one of them is, of course, the relational model. So a data model in general is about how we structure, operate, and constrain or control the shape of the data. And so it's about the structure of the data. For instance, it may specify that we have arrays like in a programming language or tables and so on, but let's say at a higher level, a conceptual model. And it's also about operations on the data. And you have to understand that unlike in a programming language, in a database data model, let's say not any operation can be performed. There will be some, let's say, limited allowed set of operations like queries, modifications that we may specify. And this is by choice. This is a strength, not a weakness, in the sense that this limitation will allow the system to reason about efficiency, to reason about query optimization, and so on. And finally, so we said structure, operations, and constraints. And constraints on the data may be conditions like a movie has exactly one title and so on. So in general, conceptually, this is what a data model should comprise: ways of describing the structure of the data, ways of describing a well-chosen set of operations over the data, and not any operation in general will be possible on the data, and ways to describe constraints, condition over the data. Conditions such as each movie has exactly one title. And besides, of course, the relational model, there are other important models, in particular, some models that we will also study in this course. There is, in particular, the semi-structured data model with illustrations such as XML or JSON, where, as the name indicates, there is some structure, but is not entirely fixed. And it's about hierarchically, let's say, nested tagged elements in a tree structure. And we will see the JSON implementation of semi-structured data and the semi-structured data model when we'll talk about NoSQL, and in particular with the practical assignment using the Apache Cassandra data system. There is the nested relational model, so-called nested tables. As the name indicates, it's about structuring the data in such a way that, for instance, the value of an attribute may be another table. This is what we mean by nested tables or a list of values. And we could also say that the data model on which the Apache Cassandra system relies is also an illustration of the nested relational model. So we'll also talk about this model as well in class. There is the graph model, of course, for describing graph data, networked data, and then, of course, the unstructured data model for describing other kinds of data such as text, image, audio, video, and so on. Now, moving forward, let's talk a bit more about database-backed applications, which are, of course, ubiquitous, and the fact that there is something else, let's say a different kind of role of database management systems that they may need, they may want, besides simply asking questions, running queries, and getting answers. Whether it is, for instance, the Uber application or Amazon or your banking application, they're all about maintaining state, about maintaining some information about where we are, let's say, in the world, how much money we have in our banking account, what have we bought on Amazon, what ride have we booked or have we paid for in Uber and so on. This is what we mean by maintaining state. And in their need, let's say, for data access, such applications such as Uber or Amazon and so on will run queries and updates, modifications of this state of the world. Different kinds of systems or statements, different kinds of, let's say, sentences or statements on behalf of many users accessing this data. Users reading and writing data, users interacting basically with the system concurrently at the same time. Over the same data, of course. For instance, we may all want to book an Uber ride from the university premises at the same time when the class ends today. And this, of course, leads to the major role of database management system, which is concurrency control and recovery as well. So here comes, let's say, into play another major role of relational database management systems, concurrency control, which is under the hood, let's say, in short, by a so-called transaction manager. And we will see that in practice, this means correct and fast data access in the presence of concurrent work by many users by somehow disorderly processing all these requests in a way that gives an illusion of order. We'll clarify what this means when the moment comes. And recovery, another major role of relational database management systems, which is about ensuring that the database is fault tolerant, will not be corrupted by any kind of anomalies, crashes, so whether it is a software or a hardware crash. For instance, if it's our database-backed banking application, if there is a crash, of course, we don't want to lose the information on the amount of money we have in our account and so on. And this relies heavily on storage, persistent storage, and certain guarantees for consistency for critical data. And we'll talk about recovery as well. So throughout these roles, I would say the system will provide general guarantees that nothing bad will happen, let's say, even if there are concurrent accesses to the data. So the data is used by different users at the same time, even if there are crashes and the system needs to recover and so on. And obviously, all this is good in the sense that it lightens, it takes load from the shoulder of application writers, from users. It makes our life basically much easier. So a question that may be reasonable at this point, you may wonder, well, why do we really need to give access to many users at the same time, simultaneously over the same data? Why do we need to run work? Let's call this work transactions, and we'll, let's say, formally define transactions a bit later. Why do we need to run work on behalf of several users concurrently at the same time? For instance, why not give access to the database just to one user at a time? And I hope the answer to this question is rather obvious. The reason is efficiency. Efficiency in terms of both throughput, that remember is the amount of work that can be done, for instance, per second. Uh, for instance, if one transaction uses the CPU, well, another one may be used to, could use the disk, and since the CPU and the disk are somehow parallel devices, both transactions could make progress at the same time, and in the end, we will deal with more transactions per second. So we can do parallel work in this way. Even more obvious if we have, for instance, a system with multiple CPUs, obviously we could have each of those CPUs work on a different transaction, for instance. And also efficiency in terms of latency, response time, simply, so remember latency is the speed at which we answer each question. And here, by allowing, let's say, parallel or simultaneous execution of transactions with enough resources, we can hope that one transaction's latency or slowness will not influence another transaction's latency. For instance, we may have a transaction that is rather slow because of um, user input that may have an unpredictable response time. Well, that will not impact the latency of other transactions that would not depend on that response time in particular. So this is why we need to talk about concurrency control for efficiency. If we didn't care about efficiency, obviously we could completely forget about concurrency control and simply say that we'll give access to the database to just one user at a time. And there will be no further discussion about concurrency control. So let's look at some examples now. It's easy to say, okay, let's run several transactions in parallel. In parallel, what could go wrong? And the answer is many things could go wrong, depending on how we execute in particular transactions at the same time, depending on how we order the various steps of transactions in time in particular. So what we have here is, let's say, a simple bank transfer done by a client from one account into another. We take 500 units from one account and we put them into two different accounts, 200 and 300 respectively. At the same time, there is, for instance, an analytical question, a query that does some kind of aggregation of all the balances found in the budget table. And of course, we would like to treat, so maybe the first query is done on behalf of a client, while the second query is done on behalf of a bank employee. And we would like to treat both transactions, both operations, as an atomic unit of work, as atomic units, all or nothing. This is what atomic means here. In particular, for instance, no partial transfer of money or no partial aggregate of balances and so on. And depending on how we execute in parallel, and here parallel is simply with respect to time parallel, let's say, depending how we execute in parallel these two tasks, these two transactions, we may in fact get totally different results. Some results that should be considered as correct, while others are definitely not correct. And we'll talk about such anomalies when we talked about concurrency control later on. And so what you should remember is that here is that concurrency is important for efficiency, but of course we need concurrency control because many things could go wrong when we execute transactions concurrently. So what are transactions? This is a major notion, a key notion in relational database management systems. It's the notion that allows us to specify, let's say, what should be executed atomically in an all or nothing manner in parallel with other work. And so this is what transactions are about. It's a major notion of database management systems. And to give you, let's say, some kind of proof or illustration of that, um, you could you can see here on this slide that there are several Turing Awards that have been obtained by database researchers over the years. So the Turing Award is, of course, let's say the highest distinction for researchers in computer science, in a way than the equivalent of the Nobel Prize for computer science. And this award has been given to Bachman for early database management systems in 73, then to Ted Codd in 81 for inventing pioneering work in relational database management systems, and then to Jim Gray in 98 for inventing transaction processing. So this, let's say, is an illustration on the importance of transactions and transaction processing in the database landscape. So what is a transaction? Well, very briefly, is a sequence of actions that are to be considered an atomic unit of work, one logical unit, all or nothing. In general, how we use or how we specify transactions, we indicate the beginning of a transaction, the start of a transaction, the set of or the sequence of statements we want to execute within a transaction, and then its end. For instance, a transfer, balance between accounts, or booking a flight, but also hotel and a car together on Expedia. All this should be executed in an all or nothing manner. So the transaction model, let's say in relational database management systems, is much more simpler than what we saw before. It's simply a sequence of read and write operations over database objects. Database objects could be, for instance, records in a table. But again, of course, the nature is the same, a batch of work that must, let's say, succeed or fail as an atomic unit, all or nothing. So it's the role of the transaction manager in a relational database management system to control the execution of transaction, and all the program logic is invisible to the system. The system will not necessarily understand that we are about to organize a trip and we are about to book a flight, but also a hotel and the car for our destination. It will simply see the work basically as a sequence of read and write of objects. This is of database objects. This is what we mean here by the program logic being invisible or not really understandable by the system. The system will only see read and write operations to and from the database. Okay, and now with transactions, the ideal, let's say, behavior of the database system is one that ensures the so-called ACID guarantees. And so a quick note here, ACID is a mnemonic, a way of remembering the guarantees, not necessarily a formalism. And it comprises four guarantees: atomicity, consistency, isolation, and durability. And I really hope that all of you have heard about the ACID guarantees in previous exposures to the field of databases. So what do they stand for? So atomicity, it's about all actions in a transaction happening or non-happening. So all or nothing. And you see next in parentheses, who is responsible for that under the hood in a relational database management system. Here, it will be the role of the recovery manager to make sure that there are no partially executed transactions, no partially executed, for instance, bank transfers or account aggregations and so on. Consistency, it's about transactions taking a database in a consistent state, coherent state, and leaving it also in a coherent state. For instance, a bank transfer should leave the database in a consistent state, in the sense that overall, the sum of all accounts remains constant. There is no money that is lost or money that appears from nothing, let's say. Isolation is about executing transactions concurrently and the fact that the execution of each transaction should be isolated from that of other transactions. So each transaction should be executed as if it was the only one working with the data, with the system at any given moment. Transactions should be isolated from side effects, let's say, due to executions of other transactions. And finally, durability. It's about if a transaction succeeds, reaches its end, commits, well, its effects should be persistent, should be safely on disk in particular, and should no longer be there should be no risk of losing the effects of committed transactions. For instance, if I'm doing a bank transfer and my web application just confirmed and I received an SMS or I received a message saying your bank transfer has been done, well, that should be the final word on it, and I should not maybe 1 hour later receive a message from my bank saying actually we did not do your, or we lost the effects of your transaction. So if a transaction commits, its effects should be persistent, should be safely saved on disk. This is what this means here. They cannot be lost, or they cannot be, let's say, immediately lost or forgotten or overwritten by some other transaction. And persistence, in essence, means writing to disk, to persistent storage. And we'll talk about storage shortly after in today's class as well. Okay, so it's time for, I believe, a first quiz in our course for you. And again, you should, if you want, you should answer in writing. Which is which? Atomicity. Is it about one, maintaining integrity constraints, all or nothing, committed data survives failures, not having to worry about race conditions? Okay, so 2, 1, 4, 3. Let's see. Atomicity is about the all or nothing, let's say, of course, execution of transactions. No partially executed transaction. Very good. Consistency, of course, is about maintaining integrity constraints. Isolation is about not having to worry about race conditions, the side effects of other transactions that may be executed at the same time. And durability is, of course, about the fact that committed data will survive failures that may occur immediately after the transaction was confirmed, was committed. Okay, very good. So now I'm done, let's say, refreshing your memory on relational database management systems and their roles in particular. And I can now move to giving you an overview of what you will learn about traditional relational database management systems in this class called Advanced Database Systems. So we'll somehow look, let's say, at the internal modular architecture of such systems, and we'll explore its modular design. A modular design, which is generally the one illustrated here, starting from the storage level and all the way to the SQL client level, the one that at which we usually interact with the database. And if to a large extent, I would say introduction to databases classes focus on the topmost level, the SQL level, databases from the user's perspective. We will look at databases from the systems and algorithmics perspective instead. And the rationale, of course, is not to prepare you or teach you how to design the next best system or best thing in database management systems, but of course, through a deeper understanding of the database management systems principles and core ideas, well, come many opportunities for us, for as end users or administrators of such systems. This is why it is important to have such a deeper understanding of how such a system works, what are the choices, what are the options, what are the risk advantages at the various levels in this modular design of such a system. So we will somehow unpack such a system and explore its modular system design, discussing each of these architectural levels one by one. What are they about? Well, in a way, of course, and this is the case in all kinds of modular design in computer science, and you may know other examples of this kind, of course. It's about each level, let's say, hiding the complexity of the one below. And so the query parsing and optimization is about this translation of the what, the question that is asked by a user, a SQL expression in particular, into a how, an execution plan that can be understood and executed by the system. Relational operators will be about formulating this how, this execution plan as a data flow on file, something that can start with data and by some kind of flowing of information reach a final result. The level of files and index management will be about working with files, blocks of data information in memory. The buffer management will be about managing memory blocks and mapping them into disk pages, blocks of information that is on disk. And finally, the disk space manager will work on pages with disks, basically sequences of bytes on some storage. And then, of course, we'll have the storage level, the database. And again, each level will be hiding the complexity of the next. This is the importance of modular design in general, and in particular for database management systems. And so if time allows, today we will start the discussion on the storage level and the disk space manager level. So we'll study data layout, how do we organize data, which logically, of course, is represented as relations, but how do we organize it into memory units? Let's call them pages of data, which must have, let's say, a primary copy of the data on disk, on persistent storage, but also a secondary copy and currently under use copy of the data in main memory whenever this data is used. And of course, in general, in main memory, the space is much more limited than on disk, and we need smart caching strategies and so on. And we'll talk about that as well. How do we pack records into pages? How do we pack fields, attributes into records? We will see that there are alternatives, options, choices that we can make at all levels with pros and cons, and depending basically on how we will use the data, depending on the frequent queries, for example, we may do data layout or caching differently. And each choice comes again with its own challenges as well that must be taken into consideration as beneficial or not for efficiency, for query optimization. We'll also talk about indexing. This is something that you may have learned about in previous classes in your undergrad studies, how to index data, and in particular in tree-like structures that will allow us to quickly find the records having a certain value. That is the role of indexing. For instance, finding movies that have the title Star Wars. Finding such movies much more quickly, of course, than reading all the data, all the movie table, one record at a time. And so we'll mostly talk about tree-based indexing, so trees that look like this, but are, of course, upside down, like that. And this will be, by the way, the topic of the second homework later on that will be posted roughly in 2 weeks' time. Indexing and data organization. We'll also learn about query execution, which we'll see uses simple, elegant operators like selection, projection, renaming, joining, operators or operations that are closed in the sense that they take as input relations and give as output relations as well, intermediate results which are also relations. And this, of course, is very important because it allows us to combine operators, to combine them into execution plans in which data, basically intermediary results, flow bottom up from one operator to the one above, starting from the level of relations to the level of the final answer. So operators that may be implemented or executed in various ways. For instance, we may access a table by reading the table, the relation entirely. This is what we call a full table scan. So reading it one record at a time, or by using an index and so on. So we'll also talk about how various operators may be implemented. In particular, we'll talk about the join operation, which is maybe the most expensive operation we may have in an execution plan. We'll see that there are various algorithms, various ways of implementing a join with different performances, depending on also on the data features. We'll bridge the what with the how, basically looking into how from a declarative specification of an information need, a SQL query, the system will decide on the best execution plan, the best plan by, first of all, charting, let's say, a space of possible equivalent plans, estimating their cost, and then searching through this space in order to choose the seemingly best one, or the good enough one, let's say. And this will be the topic of also the first practical assignment, query optimization with the Oracle database system. And we'll see that query optimization is about three different stages. So the planning space, the plan space, the space of options for executing a query, estimating their cost, and then searching through this space in the most intelligent way in order to reach the best or the seemingly best plan as fast as possible. We'll also talk about concurrency control and transactions. We'll see that when executing transactions, there is a correct way of doing things, which is easy to explain, but totally unfeasible, unrealistic, which is executing transactions in a serial order, one transaction at a time. So giving the access to the data to one user at a time, or one transaction at a time. This is, of course, simple and safe, but is totally unrealistic because highly inefficient. So the goal will be to interleave in time transactions, to execute them in parallel, and learn somehow to deal with the risks, to cope with the risks, and to allow, in a way, only orders of operations from various transactions that lead to correct results. And so allowable orders here, we'll have specific names for them, such as serializability or conflict serializability. And we'll also see implementations of basically finding orders of operations, protocols that will lead to such allowable orders, such as the 2PL protocol, the two-phase locking protocol, or the strict two-phase locking protocol. And this will be the focus of the second practical assignment on transactions with the Oracle database system as well. We'll also learn about recovering from crashes, how a system faces crashes, without, of course, risking to lose the results of committed or finalized confirmed transactions. Again, if I did a bank transfer and the database confirmed that it was done, then this should be the final word on it, okay, regardless of what may happen after, what failures or crashes may occur immediately after my transaction. And we'll see how this is achieved through methods such as the write-ahead logging protocol, WAL, and the RES protocol as well. Throughout our discussion, we'll relay some key messages. The importance of query optimization, the importance of query language, declarative query languages, the importance of structure, and we'll also talk about what lack of structure may have as implications, specifically regarding efficiency later on, or the importance of data indexing. But there are also limitations when we discuss about, when we look at traditional database management systems, relational database management systems. So we'll also discuss their limitations, their shortcomings. They have been designed, of course, already now 3-4 decades ago, with certain ideas in mind, such as avoiding redundancy and optimizing storage, simply because storage was something that was very expensive at the time. They have also been designed for single machine solutions, centralized architectures, when scaling simply meant buying a new and bigger machine in order to cope, for instance, with an increase in data size or an increase in queries, the number of queries per second. So obviously many things have changed since storage is no longer that expensive. We have seen a continuous drop of costs in disk for disk storage. It's nowadays, we could say, cheaper to store everything in an organization than to figure out what to throw away. We have seen obviously many changes in the types of data that may be collected, from data that is, let's say, obviously valuable to data whose value is maybe less apparent now, but we will keep it anyway because it may be useful later on. This is what we want to say here. We have seen, for instance, the emergence of modern web applications, including social media and user-generated content, which of course means a large increase in data volume and also the need for data analytics. And finally, we have seen growing maturity of data mining and machine learning techniques, and many scenarios that demonstrate the value of data analytics. So all these changes, of course, push us in a way towards other ideas, other ways of building and designing database management systems. Okay, so with this, the introductory, let's say, chapter is over, and starting from here, so you have a few extra slides that give a similar overview of the other main topics of our course, parallel database management systems, NoSQL, and big data management systems. Now, in order to not, let's say, disperse too much today's discussion, and also because we have limited time, of course, I will not discuss them here. I will mark them as extra slides, but I strongly encourage you to skim these slides as well, just to acquire some terminology at least, and an initial idea, let's say, on what we will see in class, what we will practice with, and so on later on. Okay, so I will move now to another set of questions, or a set of slides on the grading aspects. And again, since I'm switching slides, this is the moment to ask questions as well, if you have questions. Okay, no questions. So regarding the grading aspect, so there will be 2 written individual assignments, one on SQL and the other one on indexing and database file organizations. And they each stand for, let's say, 10% of the final grade. So 2 written individual assignments, and then 4 practical assignments that will make up for the remaining 30% of the grade, which is to be acquired before the exam. And then we'll have a 2-hour written exam, of course, at the end, covering all taught content in our class, representing the other 50%. So the first homework is on SQL, as indicated before, the language for computing a relation that allows us to separate the what from the how, allows us to specify an information in need in a declarative way. And that will enable, once again, the system to choose the best how, the best realization, execution of that question, given the context, the data, and its layout in particular. So the homework will be posted today, immediately after the end of the class, with a deadline on September 12 at midnight. There will be another homework on indexing databases, and that will be the focus on homework number 2. And then we'll talk about query optimization, bridging the what with the how the system will choose for a given SQL query, a declarative need specified by the user, the how, the execution plan for that query. And that will be the focus of the practical assignment 1 with Oracle. No, in general, the extra slides are not, of course, to be tested at the final exam. So there will be, at certain moments, there will be other extra slides, but obviously their role is to give you some more in-depth information on a topic, but all the information that is presented in those extra slides will not be part of the final exam, of course. So that, and then we'll talk about concurrency control, and we'll see that at work again with the Oracle database system. That will be the second practical assignment. And then we'll talk about NoSQL databases, and in particular, we'll focus on the Apache Cassandra database system with a practical assignment. And as I mentioned before, it will be interesting to see that in this database system, we will use a different data model, different from the relational one, a model which at the same time resembles, let's say, the JSON model for semi-structured data, but also the nested relational model, in which basically we have tables where the value of an attribute may be another table or a list of values and so on. And then we'll talk about big data management systems, and we'll focus on systems basically that allow us to perform declarative querying, SQL querying, on top of Hadoop-based or Spark-based systems. And that will be the focus of the fourth practical assignment, in which we'll use the Cloudera Quick Start package, which comes with different systems such as Spark SQL, Hive, and also the Impala system. Regarding the exam, so it will be open book, 25% of the questions with multiple choices, so QMC, and the remaining 75% short questions expecting short answers. Of course, previous exams and previous solutions for these exams will be posted on Moodle, so you will have everything you need in order to train for the exam. And in general, whether it is the homeworks or the practical assignments, we'll try to, so the teaching team, myself and the teaching assistants will try to grade them within 3 weeks from the submission deadline, and for each of them we'll post on the Moodle page corrections shortly after the submission deadline. And we'll also give, let's say, class performance indicators after each homework or practical assignment. Within 2 weeks of the publication of the final course results, also group feedback on overall student performance will be provided to students, including the grade distribution. This is something that is in general done by the MSc office. So any questions on the grading aspects? No? Okay, so if there are no questions, since it's just 2 minutes, no, actually we have half an hour, sorry. Okay, so if there are no questions, we will move now to a new set of slides. I was actually wondering how did we reach the class end so fast. Okay, so we'll move now to, we'll talk about storage. We'll talk about where sits the data. And for that, okay, so normally you should see now this new set of slides with the title, where sits the data, storage media. So before, let's say, moving the discussion to database internals, there is, of course, this aspect that we need to clarify a bit, a few notions about where sits the data, what kind of storage do we have at our disposal, let's say, in for a database management system. This is, of course, a discussion that is, in a way, orthogonal to databases, belongs maybe more to a computer architecture class, but there are aspects here that have really a major impact on database system design, and we need to understand them. So this is why we will talk about them next. So storage, of course, is a domain that has seen a lot of innovation since, well, the emergence of computer science. Many technical advances. For instance, we moved from disks that looked like the picture here on the left to disks that look like the much slicker version next to it. And also we have seen the emergence not only of magnetic disks, disks that have a reading head, like the illustration here in the middle, but also so-called flash or SSD storage that no longer have a reading head. They're still persistent storage devices, but function in a completely different way than hard disks. So we'll talk about such different options of persistent storage next. And so for our discussion, basically, we'll need to discuss three kinds of storage media. And what is different between them? Well, the top two are persistent storage. Hard disks, or yes, let's call them hard disks or HDDs on the left, and SSDs or flash disks on the right. And then main memory, RAM, which is of course not persistent, is volatile. It simply means that, and of course, I hope this is clear to everyone, when I turn off my computer, for instance, everything that is found in main memory will disappear. However, everything that is found on disk, and I probably have an SSD disk on my laptop, will be persistent, will survive this turning off, and when I turn on my computer again, I will find, of course, everything that I had on my disk before. So hard drives and SSDs are persistent storage, while main memory is volatile, is not persistent. But obviously, main memory is really important in the function of a computer. Everything that is to be used by the CPU has to be in main memory, has to be brought in main memory from a persistent storage device. So let's talk some numbers now. First of all, price. Roughly, of course, what could we buy with 1,000 US dollars? Well, we could buy, for instance, roughly 80 gigabytes of, let's say, high quality main memory, because there may be different degrees of or different versions of main memory we could look at. 80 gigabytes, while we could also buy instead 2.5 terabytes of high quality flash storage SSDs, while we could also buy instead 30 terabytes of magnetic disk, hard disk. So you can see that the prices of these three storage devices are very, very different. Now, in a computer architecture, and of course, again, this is not a computer architecture class, but there are certain aspects we need to understand. So this is where, let's say, the disk lies, whether it is the flash disk or the magnetic disk, and this is where the main memory lies, of course, much closer to the CPU in a way. And between the main memory and the CPU, by the way, there are other smaller but faster access, let's say, memory spaces, which are generally called caches. And in this storage hierarchy, we go basically from big and slow to small and fast. And in order to understand that, so at the level of the disk, of course, we have the database and various backups and so on. At the level of magnetic disk or flash disk, of course, we may treat them sometimes a bit differently. Then at the level of the main memory, we have the currently used data, simply because everything that is to be used by the CPU has to be in main memory. And then, and basically, again, we go from big and slow to small and fast. And in order to understand the differences, let's look at some more numbers. Now, instead of price, we'll talk about speed of access or latency. So when it's about magnetic disks, well, for instance, in 20 million nanoseconds, we will read 1 megabyte sequentially. That may sound slow, or because it's 20 million, or fast because it's nanoseconds, but we'll really understand what this means and put that into comparison later on. With 1 million nanoseconds, we'll read 1 megabyte of data sequentially. We'll also talk about what sequentially means shortly after. In 100 nanoseconds, we'll do a main memory reference. We'll access data in a specific address, let's say in main memory. And then 7 nanoseconds, we'll do a level 2 cache reference, or in 0.5 nanoseconds, we'll do a level 1 cache reference. And so these are, let's say, more or less the same numbers differently, but in order to understand them or to grasp the differences, the comparisons even better, we could look at, let's say, latencies in terms of little rectangles or time units. Okay, so for instance, initially, let's say, let's start with, yes, let's start here with the red rectangles. So if I want to read 1 megabyte of data sequentially from a flash drive, I will need 1 millisecond, so 1 rectangle. I will need 10 rectangles for a disk seek. We'll immediately explain what this means, basically placing the memory head onto a specific place on disk in order to read the data there. This is what a disk seek is, 10 milliseconds. Reading 1 megabyte sequentially, well, we need that much time. While, for instance, a round trip sending data from the US to Europe will take this amount of time. Now, if we if we pack basically that many green rectangles as one red rectangle. For instance, reading from a flash drive randomly anywhere on that disk will take this amount of time. Reading 1 megabyte sequentially from main memory will take this amount of time, or again, sending information, for instance, in a data center will take this amount of time. So I will let you maybe look at this later on, but I will conclude this comparison with a more, let's say, down-to-earth discussion in which we somehow we take a different perspective. Let's say we multiply uh, everything, all the latencies by 10,000 in order to bring it closer to things we do in real life. Then, with everything again multiplied by 10,000, when accessing data that is in the level 1 cache will basically take 0.5 seconds. So that's the amount of a heartbeat, the latency of a heartbeat, let's say. Now, doing a main memory reference, for instance, will be 100 seconds. Again, all these times are multiplied by 10,000. So that's the amount of time you need for brushing your teeth. Now, moving to SSDs, doing a random read, so accessing some data randomly on a disk, will take 1.7 days, a weekend. Reading 1 megabyte sequentially from main memory, 2.9 days, or reading 1 megabyte sequentially from a flash drive, 11.6 days. And then moving to the level of to the granularity of years, doing a disk seek will take 16.5 weeks, so roughly a semester, while reading 1 megabyte sequentially from disk will take 7.8 months. So we are moving from access times of the order of a heartbeat to access times of the order of 7.5 months. And I believe there are some questions. No. Oh, okay. So homework will be posted on Moodle, yes, of course. Will be posted on Moodle right after the class ends today. And I have mentioned the main textbooks for the class, in particular for the database, relational database management systems, which is the Ramakrishnan and Gerke book, Database Management Systems, the so-called COW book. Okay. Good. So now let's understand a bit why such huge differences in terms of access time between the different storage devices. Why magnetic disk is slower than SSD, which in turn is slower, significantly slower than main memory. And for that, of course, we need to understand a bit how a magnetic disk looks like, and then how an SSD looks like as well. So first of all, a magnetic disk is illustrated here, of course, in a rather simplified schema. It's basically an arm, sorry, a spindle, an axis on which we have a pile of disks, for instance, like CDs. They look more or less like CDs. We have many disks, maybe thousands of them, and we have an arm that has a reading head for each of the disks in our magnetic drive. So this disk, we'll call them platters, and these platters will spin around this axis rather fast, for instance, with 15,000 rotations per minute. So we have this pile of platters that look like CDs, let's say, and this arm with reading heads can move in and out, and this is let's say a mechanical movement in order to place a reading head on a desired track. So tracks, just like in a vinyl a disc or on a CD, will basically be represented as circles on a platter, and on each track we'll basically have our data. And so the arm will move in and out in order to place a reading head on a desired track. Now, the tracks, let's say, sorry, under let's say under the heads will make a cylinder. So for instance, here we can imagine that tracks basically at the same level will represent a cylinder of data. So what you should remember is terminology here is platters, tracks, cylinders, and the arm and the reading heads. This is another illustration of a cylinder as well. So at any given moment, only one reading head can be active. Only one head basically can read or write data at any given moment. And this is also very important to understand. Okay, so we cannot read in parallel from different platters. We also divide, let's say, tracks into sectors. And we'll talk about a certain block or page size as a multiple of a fixed sector size. I believe there is a microphone that is on from the audience. You should mute it. Thank you. Wanguru, I think. Okay, so now that we have seen, let's say, the insides of a magnetic drive, what do we need in order to access data on a magnetic drive? Well, there are several things. The time to the so-called seek time. It's about moving the arm to position the disk head on the desired track, on the track from which we want to get data. So this is the seek time, and it's roughly of the order of 2 or 3 milliseconds on average. In order to read data from a specific track, we need to make sure that the reading head is placed on that track. So this is an in and out movement. Then there is the rotational delay, because maybe the data that we would need is not directly under the nose of the reading head, but it's somewhere else on that track. And so we need to spin a bit the platter. This is the so-called rotational delay, and it's 0 to 4 milliseconds. In general, it's rather fast, but could be also of the order of milliseconds. And then the transfer time. Once we are actually, the reading head is placed on the memory units where we find the data that we want, we can read it, we can transfer it to main memory, and this is rather fast, order of 0.25 milliseconds per block of data. For instance, pages may be 64 kilobytes in size. So obviously, the key to lower access to data, which is found on magnetic disk, is to reduce as much as possible the seek and rotational delays, because you can see that these are the major delays when accessing data on in a magnetic disk. So, as a conclusion for magnetic disks, they're an invention, let's say, from another time, from many decades ago, so to speak. So this is why we say they are a mechanical acronym. They rely, in order to access data, they rely on a mechanical movement that can hardly be optimized, or can hardly be made as fast as we need it to be. Spinning the platters in a disk can be rather fast. Transferring data can be rather fast as well, but this movement of the reading of the arm and placing of the reading heads is a mechanical movement that cannot be sped up as much as we would like to. And so there are major implications of that, the fact that in a disk, we don't have, let's say, at our disposal um, methods for asking, let's say, the data that is found at a specific address. This is what we mean here by no pointer derefs. Pointer deref is the operation by which, for instance, in C, you say, give me the data found at this specific address in main memory. We don't have that for magnetic disks. We only have an API, a language that we can use when discussing with disk, which is read a page and write a page. So the unit of work for reading and writing data will be the one of blocks of data, pages, for instance, 64 kilobytes of data. So we will not have methods like that can ask, give me the value found at this address. And both methods, reading and writing from a magnetic drive, can be very, very slow. And this is why we need to plan them carefully when accessing data in a database management system. Okay, so regarding this, quick quiz for you now. Which of the following operations is slowest? Accessing all the blocks found on a single track in order, accessing an equivalent amount of data but on randomly located disk blocks, transferring an entire track of data into main memory, overwriting an entire track worth of data in main memory with something like zeros, or they're all the same. B, of course, is the right answer here. So accessing an equivalent amount of data but on randomly located disk blocks, this simply means that for each block, basically, we will need to do a mechanical movement. We'll need to move the arm inwards or outwards in order to place the reading head on the right block, on the right uh, track, and then on the right sector by spinning the platter and so on. And this will take time. While accessing all the blocks found on a single track in order, of course, this means that we only need to pay the seek time once, placing the arm and the reading head on that track in the beginning, and then simply relying on the spin of the platter in order to get all the data. So that will be much faster. One seek time instead of in option A, let's say, instead of one seek time per block in option B, obviously. Okay, now moving to the second kind of persistent storage, the flash storage, SSDs. Well, they look very differently, and in particular, they don't have a reading head. They look like the illustration here, basically a memory space that is divided into memory units. Let's say those black rectangles will be um, the granularity level at which we can read data, and then the larger rectangles, let's say the orange rectangle here, will be the granularity at which we can write data. So this is something that you should remember for SSDs. We read and write data at different granularities. For instance, we can do fine-grained reads, so reading blocks of 4 or 8 kilobytes, while writing is done coarser-grained, for instance, 1 or 2 megabytes writes. By their nature, and we'll not really talk about the physical aspects that lead to that, or by design, let's say, when we read such a small black rectangle, but when we write a large orange one. And also by their nature, there is another issue, another problem. After only a few thousand, for instance, 2,000 to 3,000 erasures or overwritings of an orange rectangle, that orange rectangle will be a dead space, basically, will no longer be usable. And so that means we need to plan things carefully. We need to plan writing operations carefully because there is this let's say, uh, phenomenon of memory units that where will be, we have this wearing phenomenon that we have to take into account. And in order to deal with that, for instance, we'll have to keep moving hot write units around. For instance, if, I don't know, this is Twitter data and there is one Twitter account that is very active, well, we'll have to make sure that this Twitter account does not sit in the same memory unit the whole time, because that will lead to dead space at some point. We'll have to move that Twitter account around in different memory units and write in each of them at some point. So this is what is called wear leveling, the strategy in order to deal with the fact that after only a few thousand erasures, such a write memory unit will become dead space. And this leads to write amplification. Writing will be much slower than reading, because when writing we may actually have to move data around in order to deal with this phenomenon. So reading overall is fast and predictable. For instance, we could read uh, at a latency of 0.03 milliseconds, while writing is not that fast. And actually, something important here, reading is fast and predictable, and there is no difference between randomly reading in a flash drive or sequential reading in a flash drive. There is no difference between, for instance, reading 10 black rectangles within this that are one next to the other. So that would be a sequential reading of 10 black rectangles. There is no difference between that and reading 10 black rectangles that are found everywhere, let's say on the disk. Okay, so random reading and sequential reading are roughly the same when we use flash drives. While of course this is not the case when we use magnetic drives. However, writing is not that fast. It's slower, in particular for random writing, obviously because if we need to write 10 rectangles that are found one next to the other, well, that means basically writing probably just one orange unit. However, if we need to write 10 rectangles that are found in 10 different orange units, well, that will of course take more time. So a single write access time is also roughly 0.03 milliseconds, but you will see the difference between random writes and sequential writes. Sequential writes are roughly 4 times faster than random writes. So another quick quiz for you here. Why might SSDs writes take a longer time? In order to postpone media failure. The transfer size is very large. SSDs suffer from write amplification. Writing a single unit might require writing multiple ones if we need to move units around, all of the above. Okay, I see many Ds. And I also see an E, which is indeed the right answer here. So if we take them one by one, obviously writing will take a longer time because we need to postpone media failure, right? Remember the fact that each orange, let's say, rectangle becomes dead space after roughly 2,000 or 3,000 erasures and writings. So in order to postpone media failure, we need to move things around. The transfer size is larger than for reading, so we saw that there is this difference in terms of granularity for read and write. Obviously, we suffer from write amplification because we need to move things around. And obviously, writing a single unit might require multiple ones because we need to move units around. Okay, so in comparison with magnetic disks, SSDs are faster than magnetic disks. Of course, it can be maybe 10 times, sometimes thousands of times faster, depending on the SSD type, depending on the magnetic disk type. However, there is a big difference when it comes to random access. We saw, for instance, that for reading, there is no difference between randomly or sequentially accessing data in flash disks, while there is a huge difference, and we saw numbers for that as well, when we access data randomly or sequentially in magnetic disks. Locality matters for both in the sense that reading or writing two faraway blocks on disk will require uh, a seek and a rotation delay, and this will be slow. Writing, not reading, but writing two faraway blocks on a flash drive may also require writing multiple much larger units. So locality matters obviously for both reading and writing in magnetic disks. It also matters for writing in flash disks. And, however, of course, magnetic disks are cheaper, significantly cheaper, maybe 10 times cheaper than flash disks. Now, when it comes to storing databases, there is, I would say, an ongoing debate nowadays on what may be the role of each of these two storage media, and that, of course, depends on the magnitude of the data. And you have to understand, of course, that nowadays, of course, many databases are not really that big. There are important databases, for instance, about daily weather, about census information, about the Wikipedia. And they are, of course, gigabytes of data in size, but not really that big. And so this is data that could very well fit, for instance, in a reasonably priced flash disk. However, obviously the reality at the same time is that data volumes grow very fast. Data sizes grow faster than Moore's law, and big data is indeed real. We can now generate and archive data very easily. For instance, an airplane may generate half a terabyte of data per flight, or in a supermarket, there may be millions of transactions per hour, leading to 2.5 petabytes of data that has to be stored, for instance, for years of activities. So in this reality, of course, what is the role of magnetic disk, flash disk, or main memory is indeed the subject of some debate. Let's say for large databases, usually what is followed is the rather traditional approach in which we still rely mainly on magnetic disks. But flash disks are making their way, I would say, and becoming more and more important, simply because they improve performance, but also because they improve performance variance. They enable much more, let's say, predictability in terms of performance. In particular, because, for instance, there is no difference when reading data randomly or sequentially. And for smaller databases, well, the situation is a bit different there because disk-based solutions may no longer be the right choice. We may instead use flash disks instead, or even we may have databases that may fit entirely in main memory. And this has led to the emergence of main memory databases in which the main copy of the data is actually stored in main memory, and the secondary copy, a backup if you want, will be stored on persistent storage, for instance, on a flash drive. Okay, and with this, with this discussion on storage media, we will stop the discussion for today. We will end today's class. Of course, if you have questions, feel free to ask. And As indicated in one of the news items that I posted on Moodle, so the office hours will start. There is this first office hour slot after this class. The way you enter the Zoom meeting for the office hours is a bit different. You will enter one by one, and you will discuss with me. And so you may have to wait a bit. There is a waiting room, and you will have to wait your turn in order to be able to discuss. So as discussed as well, I will post the homework right now in basically 1 or 2 minutes time. The first homework on SQL on the Moodle page, and you will have until September 12 at midnight to send your answers. Okay, so if there are no further questions, thank you everyone for attending today, and I will be, of course, available in the other Zoom meeting, the office hours, shortly after. Well, yes, the course will be probably online for the entire semester, for the entire duration, unless, well, the general situation evolves in a very positive way in the coming months. Okay, there is a question for HDDs. What is the order of magnitude of time for switching from one hand to another? That's negligible. Yes, yes, for the same cylinder. That's negligible. Yes. Okay, so thank you everyone. Goodbye. And so I will be reachable in the other Zoom meeting for the office hours shortly after this class.